All right. Yeah, thanks. I really appreciate you showing up, I mean, after yesterday's endeavor. So let's start really softly. Remember what we did on Monday? I was throwing various concepts from lattice gauge theory at you, and I'm using these words because I very well appreciate that this was a rush and quick and not systematic. I just meant to introduce quickly some ideas and concepts which will play a role today in our approach to strongly correlated topological quantum matter. So let's briefly recap. We decided to look at a U1 gauge theory, which is another word for electromagnetism, but now put on a lattice, in the sense that we considered a lattice which on Monday was four-dimensional, like space-time, and on each link we put a phase, just a phase, yeah? And we described the dynamics of the system in terms of a discrete lattice effective action, a discrete version of what you have in electrodynamics textbooks is FF dual effective action. And then started asking questions to the system, and we realized that since there is a gauge theory, we have to look at gauge invariant observables, and the observables that characterize the system in an interesting way were essentially non-local. They were the version in this system of the Wilson loops you have seen so often in these lectures, by other lecturers. And within this framework, we then hinted at the existence of two phases. One in which the phases fluctuate rapidly, like hell, some kind of strong coupling phase in the jargon of field theory, where the prime indication of this behavior was the confinement of electric charge, something you will not see in a continuum electrodynamics. You try to pull electric charges apart, and in this system, if the phases fluctuate strongly, you have a linearly increasing attraction like with quarks. Yeah? So that was one phase. The other phase was one where the phases fluctuated only weakly and charges were deconfined. Yeah? So this was. So what do we do today is we play a very similar game, but much simpler. It will be simpler in the sense that we now replace our U1 gauge degrees of freedom, the phases, just by binary variables, Ising variables, plus minus 1. So formally speaking, instead of U1, we consider Z2, yeah? Ising variables. Second, instead of a 4D lattice, we go to a 2D lattice. That's also simpler. And instead of using the effective action description, which is efficient but perhaps somewhat abstract, we directly work with quantum Hamiltonians. So we work with Hamiltonians. I will give you a Hamiltonian of the system. And this is essentially a change of language. And you find this, this passage here worked out nicely in Kogot. So you can decide to work with Hamiltonian or effective action. Again, we will have to look for non-local observables. I mean, they will be our friends to study. And again, we will have two phases. Yeah? In this system here, it turns out that the confinement phase exists, but it's not so terribly interesting. The deconfined phase, however, and that makes the system different from U1, is topological. So this one here is a topological phase. It's a strongly phase showing strong entanglement, and it is the archetype, I mean the ancestor of all topological phases that are out there, at least in bosonic gap quantum matter. So this is the harmonic oscillator of strongly correlated topological quantum matter we're doing here. Yeah? Okay, so that's the program. Now, how do we do this? I mean, how do we get an interesting Z2 gauge theory? Yeah? So let's start with something everybody knows. I mean, here's our lattice. I hope I will not erase it in some panic mode. It will stay there. And here live our Ising variables on the links. Yeah? Now, one thing we can do, I mean, you know that from textbooks, you can just write down an Ising Hamiltonian. Here it is, nearest neighbors, I mean, this and that, and this and that. Sigma Z, and I'm using here Pauli operators, yeah, Hamiltonian level. So that is a nice Hamiltonian, and you know it from the textbooks, and it has a global Z2 symmetry, global. Meaning that if you flip these two, I mean, all operators, all sigma z's into minus sigma z, or all states into their minus, the Hamiltonian remains invariant, yeah? Trivial. So Wigner's idea in the beginnings of the 70s was to formulate a Hamiltonian of very similar flavor, I mean, almost as simple, but having a local Z2 symmetry. And I show you now this Hamiltonian, and I explain then in a minute why it is, in what sense it has a global, in fact, an infinite dimensional symmetry, the gauge symmetry. So the gauge Ising Hamiltonian, this is the guy we are addressing today, has the following form. We sum over all plaquettes of the lattice. I mean, we sum over all these checkerboard plaquettes. And we do that, we give this term, there's a coupling constant, lambda. And then we just take the product of all Ising variables around the plaquette. Like what we had, remember in this U1 business, we took this products of phases. Now we take the products of Ising operators. So something like sigma z ij, sigma z jk, sigma z kl, and sigma z li. If I, j, k, and l are here the lattice sites, I mean I, j, k, l, yeah? And summing over all plaquettes. So that is, it's a product of 4, yeah? I mean, I can write this here. Sigma z l I. Okay? That is one term in our Hamiltonian, and I explain its physics in a sec. There is another term which we add with a different coupling constant, and that one is defined just on the links. I mean, on the links, we take the sum of all link sigma x operators, sigma x. So it's a bit like transverse field Ising, sigma x I. And that is the Hamiltonian. That is the Ising gauged Hamiltonian. In the jargon of the field, in the jargon of the field, this term here is called the electric term. This is like, we call this electric. So it measures electric flux. I tell you where this terminology comes from. And this one here is called magnetic flux. Z2 magnetic flux, magnetic. Where does this terminology come from? If you start from a U1 electrodynamic theory, which is obviously electromagnetic, and reduce from an effective action to a Hamiltonian action, or to an Hamiltonian, you discover two terms of very similar architecture now for phases. And one is the ancestor of electric type of part of the action, and the other one is magnetic. And this here is, you see, it's like a flux term, and this one is a bit like flux with a link. So it's just terminology. Yeah? Now that is the Hamiltonian, and it was formulated in the early 70s, as I mentioned. And what's interesting is that throughout, in the course of time, in every decade, this Hamiltonian reappeared for different reasons of motivation. Yeah? In the 70s, we lived at a time when there was stat mag around, lattice gauge theory, particle physics, and the confluence of all these motivated lattice theories of this type to study. That was the 70s. In the later decades, maybe 80s, 90s, people observed that effective Hamiltonians of this type are very often born out of the physics of fractionalized, strongly correlated quantum matter. So there was a physics of magnets and so on, and very often the effective degrees of freedom were fractionalized at 2 degrees of freedom, and Fisher and Zentel and many others wrote on this guy. Yet later, 2000s, this Hamiltonian was very popular from the perspective of topological quantum matter, but also quantum info. This is the Hamiltonian of the toric code you see here in this guys. Yeah? So, and let's try to figure that out. I want to stress this info topological aspect today. So now let's first understand why this Hamiltonian has a lot more symmetry than the Ising Hamiltonian, and this symmetry, the presence of this symmetry, or what should say gauge redundancy, that is the source of strong entanglement in the system. Yeah? The point is, we can define, besides the Hamiltonian, an infinite class of operators for each lattice point, 1. So independent operators that all commute with the Hamiltonian, so have a huge symmetry in the problem. And these operators are defined as follows. Where are you? I call them rho I. They are specific to each node. We have one of them. And what we do is we take the product of all j, sigma x, I, j. Oops. So what this rho I does is you pick a site, and you build the product of all outgoing links, yeah, and multiply sigma x. And this operator here is called the charge operator. You can smell why it has something to do with charge. I mean, this was electric field, yeah? So we're computing here the outgoing electric flux, and by Gauss law, the outgoing electric flux equals the charge sitting in the middle. So that is the analogy, why it's called charge. Otherwise, it's just a name tag. Okay? And what I'm claiming now is that individually, these guys all commute with the Hamiltonian. All independent, yeah?
So all the sums and the products are just for the first neighbors, right?
Yeah. So here, it's a star-like object, sigma 1, 2, 3, 4, this is what you build, all axes. Okay, so these are our operators. And are there more questions, perhaps? Question? Nope.
Alex,
Yeah.
the first line in the electric part,
Yeah.
is it just only one term, or it's already...
Only one. Yeah, the question was whether it's only one. This is summing over all links sigma x, nothing more. Huh? Yeah, somebody else besides me can do that. Yeah, sure. Yeah. So why do we have this property? It's actually easy to see. See, these are just sigma x's, so they trivially commute with all sigma x's here. Pauli operators commute. And here, the way to see it is as follows. Suppose you have a plaquette, and you build the product of all sigma z's. Now you can consider a charge operator somewhere else, which would trivially commute with that plaquette. Interesting thing happens if your charge operator is sitting here, and this is the plaquette in question. You build this commutator. But then, sigma x flips sigma z. Just flips it. So what the charge operator does, it flips this sigma z and this sigma z. It flips two of them, always two. And in a product of 4 around the plaquette, these two sign changes always go out. So they are mutually commutative, these operators. Now, another thing we can say is that this sigma x here, if it sits here is precisely the generator of a gauge transformation. In the U1 context, what was gauge transformation in the U1? We picked a site and we shifted all neighboring phases, yeah, or by some continuous parameter. What we are doing here is we pick a site, and since we don't have continuous phases but still want to shift, the only thing we can do is shift +1 to -1. This is a discrete gauge transformation, and this is precisely what this guy does. So yet another way of saying is that the generators of gauge transformations in electromagnetism are charge operators. So this Hamiltonian is now charge conserving and locally charge conserving, and hence gauge invariant. Yeah, is that clear? It's a huge symmetry. What we want to understand now is the consequences. And in particular, we want to understand why there are, again, two phases in this Hamiltonian. And these two phases are now, which one wins, on which side you are, that is adjusted by the ratio of these two coupling constants, whether you're in an essentially electric or essentially magnetic phase. And our friend is this one here. That's the interesting one when this wins. So let's introduce parameter R equals lambda over gamma. And I claim now we have a confining phase. Confining, and that is R much smaller than 1, smaller than 1, meaning that the electric term wins. And the second one, the deconfined phase, is the magnetic phase, where the magnetic term wins. This is the deconfined. And what I mean by confinement is here, this is a local charge operator. And let's, the Hamiltonian conserved charge. So you can give me a charge number and we can work in the corresponding sector of Hilbert space. Now let's suppose we are in the sector of, starting in the sector of zero charge, neutral system. All these guys are always positive in our Hilbert space. And it would stay like that. And then we put artificially, externally, 2 test charges into the system. And we ask what their fate is. Yeah? And we can ask this question in the limit where this is strong or where this is strong and get very different answers. So let's first switch this term completely off. That is the extreme limit, extreme confining limit. We have only electric correlations and ask what happens with 2 charges. Yeah? So suppose I do the following. I consider here a site where one of these sigma x eigens, now I'm working in sigma x basis. Yeah, that's preferable, and I can always decide what basis I'm using, whether Pauli is z or x. Now I'm considering in an x basis here a site where one sigma x is -1, all others plus. So that means that I have a charge sitting here. But if these are all +1, it would also mean that the charge is sitting here, because that one's also -1. But I don't want this. I want a configuration where, say, we have charges here and here. Yeah. So, in order to realize a situation where I have charge -1 only here and here, but everywhere else -1, I have to flip a few sigma x's. So I need to consider something that is called a string. And what this string means that everywhere on each link I flip sigma x. If I flip sigma x here, for example, here and here, this one again has charge 0 because I have an even number of sigma x's flipped. Here also even, charge 0, charge 0. Here's charge -1 and here's also charge -1. Do you get this? Yeah? I need to consider a state. If my rule of the game is charge operator has an eigenvalue -1 here and here only, and I work in the sigma x basis, then I definitely have to have such a configuration where I have a few sigma x's flipped. This is essential. Please ask if this is not clear. Huh? Yeah, no problem. Let's work in the sigma x basis. Sigma x. So each link gets a label +1 or -1, depending on sigma x value. And I'm testing these operators here. And I want a configuration where the eigenvalue of this operator, this is in the eigenbasis now, is -1 here and nowhere else. Then I'm claiming that I cannot work with a configuration where all sigma x's are +1 here and make the Hamiltonian happy. Because, say, if they were globally positive everywhere here, and I would have only here a -1 link, then I would have charge -1 here, but also here. Because here I would build +1, +1, +1, -1, -1, and here +1, +1, +1, -1, again -1. But I want this to happen only here and here. So the only way out is to flip sigma x's and to invest such a string. So along this string, all sigma x's are now -1. The charge is happy. What is not so happy is the Hamiltonian. The Hamiltonian, because for each term where you flip the sigma x, you have to pay this price of gamma, and gamma is large. Well, finite. So that means that the more I pull my charges apart, the more energy I have to pay, and that is the physics of confinement. It's a linear growth in energy, and so charges are strongly confined.
If you're in the sigma x basis, if you're in the sigma x basis,
yeah.
the electric term doesn't flip.
No, it doesn't flip. My sources flip. The observable. Remember, I want to work in a Hilbert space sector now, in which I have a charge here and here. And in this Hilbert space sector, I have to have such a string present, and it's determined by the space in which I'm working, not the Hamiltonian.
But you say that's the gamma that controls the energy of the string.
Yes, right, precisely. Here, this I don't know if this answers the question, but this is my Hilbert space, and I can organize it in blocks of different charges. And in each block, the Hamiltonian is fully diagonal now, because it does only the energy counting. And what I was saying is that in a sector where I have global charge 0, but 2 local charges sitting, my Hamiltonian will indicate that this costs me energy. It's just the energy counting that the Hamiltonian does. Yeah. I mean, I'm just working in the eigenbasis of this problem now. So that is the analog of the confinement phase in the one case I described earlier. And I introduced this essentially for completeness or illustration, but now I want to switch to the complementary scenario where we have deconfined. And that's actually a neat one. And introduces, that was not good, introduces right away the ideas of strongly entangled topological ground states in string nets. I think it's quite cool, actually. Product over J, sigma x, y, J. So let's now consider the opposite case. The electric field term is absent, and only the magnetic term is switched on. Here, so this is gone. And now I have to make this term happy. But I always work in a sector of definite charge. Yeah, I want to work in a sector of Hilbert space of definite charge. And since these commute, I have to simultaneously diagonalize this Hamiltonian and that, all these terms individually. Yeah? So let's try. A good way to make this one happy, now we work in the sigma z basis. Yeah? A good way to make this term happy is to tell every sigma z to point up. This will obviously be happy, all spin ups. And let's denote this term now by a white lattice. White lattice means all spins pointing up. Okay? Yeah, all spins pointing up. It's obviously a ground state of this Hamiltonian. But unfortunately, it's not a charge eigenstate. It's not a charge eigenstate. Why is that? Because suppose I start with this is my ground state now, yeah? Everybody pointing up. And I hit it with any of these operators, then these operators change the state. Because what will this operator do? Say, I have here my I, and I hit the state with a rho, I will flip all these guys. The good thing is that these operators actually commute with the Hamiltonian, so I don't pay in energy. It's still a ground state. Why? Because if, say, this plaquette was previously happy, it will be happy even after, because I flip always an even number of links here. But I changed the state. Got this? This is, again, one very essential one. So now let's try to construct, because, I mean, these commute, we have to be able to find a simultaneous eigenstate of these operators. So let's try to compute it. And the good way to do this, and that's a stringnet way of thinking in topological matter, is to so construct a ground state. We start from a vacuum, which is symbolically all guys pointing up, I mean, in a sigma z basis. And now we just start hitting it with rows. We just see what we get. Yeah? Suppose we hit this state, we consider rho I 0. What will we get is a state which, yeah?
Could you just define the product of J? I can't remember.
Yes.
Product is all the...
It's over the nearest neighbors here. Yeah, how to write this? I mean, the best way to, is not to focus too much on the formula, but on what's going on. So you pick an I, this is this one, and build the product on over all four links. Yes. It will not change. I mean, it's always this. So let's try to ask what this guy is. A way to represent this, and this is a graphical code which I will present in the following, is this guy flips all sigma z's on the bonds neighboring to I. And the way I will represent this is just by drawing here a little blue square. So when you see these blue lines, what it means that at every sigma z crossed by a blue line is flipped from +1 to -1. So this is the state, this state here.
Can you show it yellow? Do you have
Yellow. Blue is a bad color. Actually, I learned from Franz Wegner himself that I must never use green. But blue was not, I thought I honor his heritage by using blue, but he's not dead yet, but still. Better? Good. So that is the state. Now, just for the fun of it, we can keep hitting our state with more row i's. We just add a few more. And what we will get then is configurations like this, or maybe even that here. So we get a superposition. We got all kinds of loop configurations on the lattice. Yeah? And now you get the idea of writing down candidate ground state. So I'm writing down a ground state. And this ground state is simply, there is no good formula for representing it, but philosophically it's the equal weight superposition of all possible ways of hitting this state with rows you can come up with. So every possible combination of row i's, infinite products, is realized with equal weight. Yeah? So something like big sum, big products, hitting 0. And the important thing is that here you have the same prefactor. Unit equal weight superposition. It's like in superconductivity. When you construct a BCS wave function, it's done in the same way. You build equal weight superpositions of Cooper pairs. Now it's just these guys. So this, I claim, is number 1, a ground state. We saw that. And number 2, it's an eigenstate of charge. Because if I take another charge operator and hit again, it's already represented here. So nothing changes. Yeah? So this is an equal, not philosophically, the pictorial way to think about it is that the ground state is now a spaghetti of closed loops on the lattice. Arbitrarily many, non-branching, not intersecting, just all possible closed loops. And you add them up with equal weights. And this is a ground state. It's charge conserving, gauge invariant, because it doesn't change under these generators. It's a ground state, and it's called a string net. For obvious reasons. This is a net of strings, yeah? Yeah?
So the idea is that you can have a chain of this operator transforming a string, but let's suppose that you patch the full network. If you patch the full network
yes.
in a fashion that is not crossing, then you have changed the sign of the full system. Is this a ground state?
What did I change? The size?
The sign. If you make a string that is patching the full system.
Did I tell you periodic boundary conditions? Periodic boundary condition. So this is a torus. It's called toric code because it's a torus. So it's a toric lattice. Very good question. And I'm coming to that. I'm coming now to this issue of boundary conditions and so on.
No, even if you think without boundary, you can imagine a string like a piano curve that is covering the full lattice.
Yeah.
And somehow in this way you are changing the sign of all the nodes.
Yeah, sure, but it's compatible. If I have two crossings, I have no crossing. Yeah. So if I take loops, say 2 of them that touch.
Okay, so if you patch the full system, you find again the same ground state.
Yeah, of course. It's a similar. Yes. Yes. Answer is yes. Good. Is that clear? That's the idea of string net constructions. So these ground states, look how they are. First of all, they are, where charge is concerned, they are now deeply deconfining, yeah, because I have sigma x flipped everywhere in arbitrary combinations, so it's a total chaos. In the charges are floating around wildly, but the whole system is neutral. So it's overall neutral. It's constructed in this way, and that is about as much as we can say about the ground state. Yeah.
Like how big is the degeneracy?
Very good. I'm coming to that. That's a key next issue. Right. Very good. You can ask the ground state, or are there others? Is this the only ground state? And that's now getting interesting. The statement is this is a topologically ordered system. And the way to see it, yeah, there are different ways to see this. The first is you can do the following exercise. Ask yourself, is a ground state unique? And in order to figure that out, is you take a lattice, two-dimensional, of a certain topology. I mean, this could be torus or a torus with various handles. Yeah, you just patch them up with a square lattice. And now you ask yourself, how many degrees of freedom do I have? Obviously, one per lattice link. But to be in the ground state, I also have constraints. I have to make these guys happy, and I have to make these guys happy. So if you do the counting, and you find that worked out in Kitaev paper 2003, I can give you the reference, you will actually find that there is a degeneracy. So you have lesser constraints fixing the ground state than you have degrees of freedom. And the degeneracy is determined by the Euler characteristic of the manifold on which you're working. So it essentially goes like 2 to the number of holes you have in your system. In particular, I mean, this is abstract formulation now. A torus with just one hole has a 4-fold degenerate ground state manifold. And I want to explain why this is the case. This is easy to see without combinatorics. You can easily understand why this is the case. And the hands-on way to diagnose ground state degeneracy is now to come up with Wilson loops. Yeah? No, much simpler. I'm just telling you in the ground state sector, I mean, satisfying simultaneous ground state here and charge neutral, I have not one, but I have 4 states. 4 states, which are all, if I do my brutal loop representation here, I get the equal weight linear position of all 4 of them. But in fact, the sum decomposes into 4 sectors. And each one individually is a ground state. So that's where the degeneracy comes from. And it's easy to see why, and their presence is diagnosed by Wilson loops. I mean, Wilson loops, gauge invariant observables, which you can test. And I'm coming up now with the following loop. I built a loop which I call sigma z A. And A runs now from 1 to 2. And it's done in the following way. Now I need another color. Yeah, red. Red is allowed, yeah? Okay. So I built a loop operator cutting through the lattice like this, and we are now in a torus. We're having periodic boundary conditions, yeah? So it's a closed loop operator, and it's built like product over this contour here. This is contour A equals 1, all sigma z's. Sigma z, product over CA, sigma z ij. Yeah, I mean, just sigma z, sigma z, sigma z. And there is a complementary operator which I built by, actually let me call this here C1, and this here is C2. Okay, another Wilson loop of this type. Yeah, no, it's the same thing. So A equals 1 and 2. So we have 2 Pauli operators sigma z constructed, and we can read them out on the ground state, on our states. And what I'm saying is that these operators here, the values you get, are topologically conserved. They are these are non-local conserved operators which stabilize individual ground state sectors. And the way to see that is as follows. Suppose you start with a given configuration of these, yeah? And now you start hitting with these guys. These are the ones that actually change something. So whenever you take a yellow loop intersecting any of these lines, it will always intersect twice. So because, you know, I mean, you do this, and that, 2 intersections. So, and here again, no, 0 intersection, which is also an even number. So whenever you hit with a loop, you do not change the eigenvalues of these ones here. And that means that these operators can be diagonalized in the, it's called computational state, in the jargon of state, in the ground state space. And they assume now two different values independently, this one and that one, and this gives you a fourfold degeneracy of the ground state. Okay? Yeah? Because this one can assume the value plus minus 1, and this one can independently assume the value plus minus 1. So you have a 2 times 2. The eigenspace of, these are two Paulis, and each one is 2 times 2 equals 4. Now, once you have these here, it's a good idea to introduce two more operators which are massively non-local and change the ground, flip one ground state into the other. You know, you have now, it's clear that no local perturbation will change this eigenoperator, but now we introduce non-local operators which do change their eigenvalues, and they are obtained by, I must not use blue. Taking an arbitrary line here, no matter which one, and just cutting through like this. This and that. And these are all, by definition, this is the product of all sigma x's along these links. Yeah, I just defined this. So I define the following. Sigma xa, and A also runs from 1 to 2. As a product over Ca prime, these are C1 prime. This is actually C2 prime here. No, C1, C2, C2 prime, and this is C1 prime. Yeah, exactly. They're different. 1 and 2 come in different orders. And you build the product of sigma x. So all sigma x is intersected. And why do these guys change? Say, this operator, if you apply it, changes the eigenvalue of that. Why is that? Because at some point it will hit, and you apply sigma x here, and it changes the sigma z eigenvalue of this one. Do you get this? I mean, this one doesn't do anything, this one doesn't do anything, but this one here does. It flips one sigma z along this line, and therefore changes the value of this operator. By itself, it's a closed loop, so it operates in the ground state. Yeah? So it's a, yeah?
If you change the eigenvalue of the loop, is the loop stay closed?
Yeah, they are all closed. This is it.
If you add that, you still keep it closed?
Is it? Yeah, here, this is site 0, and this is again site 0. So I have periodic boundary conditions. And imagine this wrapped up.
Yeah, but if you add from the middle of like the state,
Yeah.
Yeah, this is still closed, right?
Yeah. I'm just saying I'm staying in the ground state, but if you build the commutator of these two, because they have one sigma, one operator in common where we are sitting on the same link, I have a commutator or anti-commutator 0, yeah? So it changed. Here, this one contains along here, all these here are irrelevant, yeah. But here you have, in this operator, you have sigma z sitting. And coming down here is a sigma x flipping here. So if you build the commutator, you build the commutator of a sigma z here and a sigma x, and that gives you, anti-commutator is vanishing, so you flip. That's the idea. So what these operators are, in this quantum info context, they operate in the topologically ordered ground space, yeah? And they define a little Pauli algebra. You have, tensor product of two Pauli spaces here now, and in the jargon of the field, in stabilizer called quantum computation, these sigma x's and so on, they are the physical qubits that are built in the lab on a lattice. But these are the ones that store information. And the idea is now to encode quantum information, to encode it in a huge space So you pay a large redundancy, you invest lots of physical qubits, and in exchange get a small number of information qubits, but they are highly protected because to change any of these, you have to apply an operation that is non-local in the language of the physical degrees of freedom. Yeah? So that's why a little bit of decoherence acting here doesn't do anything to it. Yeah? Yeah, very good question. Tori code is, of course, artificial, yeah? That's the question. Nobody, but in quantum info, these are called surface codes. So the story is that if you are in the lab and you have, say, superconducting qubits or Majorana qubits, you can come up with boundary conditions that effectively mimic the periodic boundary condition. So you just have to cut in an intricate way. And then you have get what is called a surface code or stabilizer code. Yeah. Yeah, you cannot do that by any. This one. Yeah, but then you, if you don't want, you're not allowed to cut. Yeah, no scissor. Yes, but then you get two loops going around. But two loops are equivalent to no loop. Because then you go down, I mean, if you this is what you have in mind, right? I mean, to pull it here all the way up, but then it goes down twice. And since it goes down twice, it cuts this line twice, which means nothing. That is actually, I mean, we had Joel Moore with cohomology lectures. What's going on here is actually applied cohomology. Yeah? You ask, if you don't know what cohomology is or how it works, this will sound cryptic, but it's all about this topology of surfaces and boundaries. And that's the beauty of this field. I mean, all these fields touch and nobody understands really the whole picture. I mean, including myself, you always see these glimpses. So this is applied cohomology. And this is as much as one can say about the ground state of the system. Now there is one final little, 10 minutes or so? 10 minutes? Or 20. Gosh. Yeah, well, I probably don't need to. The final thing I want to discuss is that of topological excitations in the system. So you can start to ask yourself, what are finite, I mean, non-extensive excited states? I really have to mess with my... Yeah. So it's repaired. Yeah. The thing here is that there are two fundamental types of excited states which you can create, which give you what then become topological quasi-particles on anionic excitations on the lattice. And they're easy to understand. The first one is called a magnetic excitation. What the magnetic excitation does, it makes this term here locally unhappy. And it goes like this. I mean, let me draw it and then you understand. We pick two points on the lattice and construct, no blue. 2 points on the lattice, yellow, and construct a string between them. And the string as always means sigma x, application of sigma x. So you see, no big deal. Here, for example, I have two sigma x's, flipping sigma z twice, so the magnetic term doesn't care. It doesn't care here and here. So this is I don't have to pay for the extension of the string. The way I have to pay is here and here. Because here I have only one sigma x crossing. And previously, this plaquette was happy. All sigma z's have product 1. But now, because I'm acting here with a sigma x in my string operator, yeah, this plaquette will be unhappy. And this one as well. So I pay a price of twice lambda for that. And magnetic excitation, they are called magnetic because they make this magnetic flux unhappy. Magnetic excitations categorically come in pairs. You don't get them in even odd numbers. You have to have a pair. So the corresponding operator is called M in yellow. And it's just the product of sigma x's along a yellow string. So product sigma x I j along the string. Okay. Now there comes the second excitation, second class of excitation. They are electric in nature, and you can guess what happens. The electric excitations are products along really the length of the lattice of sigma z. It's always the opposite order. So you do something like that. You pick a lattice side here, say, and here, and draw again a string, but now on the lattice, not cutting the lattice. And write down E, again, product over the string, sigma zij. Okay, now you ask yourself, how much do I have to pay for that? And the answer is no, nothing. Because see here, 2 sigma z's, and anyway, it's sigma z, so the magnetic term doesn't care at all. In order to make them pay, you have to do the following. You have to add charge with a bit of chemical potential to your Hamiltonian. You can do that because it's diagonalized anyway. So you, instead of considering H, you consider H plus constant times charge. And then you have this term in the Hamiltonian, and this term doesn't like what we are doing here. Because, see here, I change something, and here as well. So in this case, I have to pay energy for them. Right. And how much do I have to pay? Again, only for the terminal points, yeah? Because here, say if the charge operator here has these 2 sigma x's in it, so it doesn't care. But here and here I pay. Is that clear? So these are the excitations in the system. And now you can do the, once you have them, you can play the notorious games you do in 2 dimensions, so you have topological quasi-particles. I mean, they're again protected to a high degree. And realize that they are considered as point-like particles. You can move them on the lattice. But they are always realized as endpoints of strings, yeah, philosophically. So question you can ask is, what kind of quantum statistics do they have? And for example, you can take this particle here and wrap it around that one and ask, will you get back to the same state? And you will not be surprised if I'm telling you that, yes. I mean, these are bosonic. And the same with these. They are also bosonic. But more interesting is what happens if you take a red one and take it around a yellow one, a magnetic around an electric. And that is actually not a fermion and not a boson, it's a semion. You get an exchange factor of, a full rotation gives you a -1, and a half rotation in a way gives you an I in this sense. And the way to see it is, if you take this one here and wrap it around that one, there will be a red line crossing a yellow line, and that gives you a sign change. And now you may be confused. Sign is also what I expect from fermions, but you have to notice that quantum exchange statistics is actually always going around a semicircle and then translating. I mean, I'm a bit quick here, but so what you get is only half the phase you get for a fermion, and that's why they are semions. So, yeah? Oh, in the lab, you can do that by just adding another, you apply, say if these are Majorana qubits or whatever, you apply Pauli sigma x here. And in this case, the dot moves up.
So you really extend the
yes.
around the...
Yeah. You do just this. I mean, apply lots of physical qubit operations and And then there are the smarter schemes like braiding by measurement and all these high-minded things you can also do, but in essence it's this. So this now defines a little fusion category of different quasi-particles, and one amusing thing you can do is you can actually consider kind of confined strings, like you take magnetic here and electric here and consider a double string. And if you do that, you actually have a fermion, because now you have two of them combined. And if you wrap them around, because it's a double string, I mean something like a worm, you have a fermion. And at this point, you can get philosophical. If you can read Venn's textbook on that. Venn gets very emotional on this. So what you observe is we started with a theory that was fully bosonic. Yeah, it was arguably just Pauli operators. And what we find is that in its excitation spectrum, we have fermions. And these fermions always come as pairs and always come as endpoints of strings. And so you can start wondering if this is some kind of baby string theory picture, which is compatible with the idea that the fermions in the universe are emergent quasi-particles and that they're in fact endpoints of strings instead of point-like and so on. And so one gets these funny ideas. And again, read Ben. It's very entertaining to read what he has to say about that. And yeah, I guess that's a good point to stop. Thanks. Yeah, very good, very good. As long as you're two-dimensional, okay. 3 dimensions is a different issue. I mean, you know that topological classification in 2 dimensions is reasonably well understood now. And there is this famous paper by Levin and Venn that does this. So in 2 dimensions, mostly when you really go fundamental, people work with trivalent lattices, with honeycomb lattices and work there. You can do the same story there, and it's exhaustive. And you can try to classify string nets and so on. 3 dimensions is a totally different story. So in classification problem in 3 dimensions, for all I know, is not well understood, and we have these interesting activities. And there is deep mathematics connecting that, a theory of 3 manifolds, and in 3 dimensions and up, it's all out. That's for you guys to figure out. Yeah. Yeah. Mm-hmm.
This picture looks kind of similar to what we had yesterday's lecture, where we had the one-year chart cycles on one axis and the other axis. So, except that there was a single invariant there.
It may have been one of the lectures where I actually went surfing. So I'm afraid I may have missed that lecture, so I cannot comment. Which one was that? By whom?
The extension of Andrei Excitation from the one-dimensional.
That was Andrei number 3.
Number 2.
I was present in Andrei number 2. So what was in which one?
3 still has to come.
Hmm?
Yes.
Well, 3 is today.
3 states.
I mean, was the extension of the 1D chain with inversion to 2D?
No, but he did that in the 3rd lecture because I told him I was a chairman not to do it in the 2nd one. His time was up.
He's planning to do the honeycomb lattice.
In the 2nd one?
Oh, yeah, the third one in 1 hour.
Oh. Sorry, I must have had a blackout. No, nothing intelligent to say. Yeah, 0. Point.
I mean, the winding around the manifold is...
That one. You mean in this unit? Yeah. Hmm?
Except that we can here wind in 2 directions.
Yeah. No, absolutely. Yeah. This. Yeah, these are. You're totally right. You see, I mean, there is a zeros order picture underlying all what we are doing here, and this is it's actually a very well invested time to read what mathematicians have to say about gauge theory. For them, it's always one picture. You have one base manifold, which in his case is, I don't know, this lattice, and here it's another lattice. Then you have degrees of freedom, which are fibers, and you want to move degrees of freedom, and there is a trivial structure underlying, so you come up with some trivial, non-trivial parallel transport. in some cases, it was a ground state projector here. Here it's a different one. And this parallel transporter, which gets you from one to another, is, if it's closed, is called a Wilson loop in our language. So we all do play the same game. It's conceptually, it's just different settings. Yeah.
I mean, my question was that how would the extension of this to continuum limit do by doing any other complications?
Very good. Continuum limit of this, in case you know, is double Chern-Simons theory. So it's actually a brilliant question. There is a Venn paper, I can give you the reference, 2006 or 8 or so. You ask yourself, what do I get in the continuum? And in the continuum, I get copies of Chern-Simons actions. We have two-dimensional in real space, one time dimension, so you are three-dimensional. And the Chern-Simons does a bookkeeping on the exchange statistics. So this is, in a way, a lattice implementation of Chern-Simons, much as the lattice gauge theory was a lattice implementation of continuum electrodynamics. Yeah, it's an excellent question, yeah. Mm-hmm.
Yeah, well, I had the similar question, so.
Just integer levels.
It's for two semionic quantum particles. So there is this K matrix which does a bookkeeping. And for other string net, I mean, all string nets, there is also branching string nets, right? I mean, you have string net theories where you don't have closed loops necessarily, but they can branch out and they can have different colors and God knows what. The continuum theories are always Chern-Simons of non-abelian Chern-Simons. Okay, well.